Imagine this. A single discovery that explains how our bodies use oxygen, how a candle burns, and even what happens inside a star. What could this simple yet all-encompassing theory be? In 1901, the Nobel Prize in Chemistry was awarded to a scientist who unraveled the mysteries of combustion. But this wasn't just about a match catching fire. This breakthrough unlocked the very heart of chemistry itself. So, what makes a substance burn? Or rather, what is combustion really the result of? Let's journey back to the early 19th century to find the answer. Ready? Here we go. Jacobus Henricus van T. Hoff. His name might sound a bit complex, but his work? It transformed the entire history of chemistry. A curious childhood and a rebellious mind. Born in 1852 in Rotterdam, Netherlands. As a child, he was a bookworm but despised textbooks. His teachers called him dreamy and undisciplined. Once, he was caught scribbling poetry in his notebook and was suspended from school. Blending imagination with science. Van T. Hoff grew bored with traditional education. He sought to understand nature not just through books but through the lens of his imagination. He fused chemistry with literature, even writing some chemical formulas as if they were poetry. At 17, he wrote in his diary, "Without imagination, science is nothing but dry rules." A European quest for knowledge. He studied in cities like Berlin, Bonn, and Paris. Guess who inspired him the most? None other than Hermann von Helmholtz. During Helmholtz's lectures, Van T. Hoff didn't just take notes, he sketched vivid illustrations of his professor's ideas. A scientific breakthrough at just 22. At the age of 22, he published a paper that shook the scientific world to its core. The topic? The three-dimensional structure of molecules and the spatial arrangement of atoms. This laid the foundation for what we now call stereochemistry. But his revolutionary ideas were initially dismissed. Almost everyone opposed him except the French chemist Charles Adolphe Wurtz. The renowned German chemist Hermann Kolbe even wrote, "This young man should write less poetry and spend more time in the lab." The ultimate irony, isn't it? Years later, that so-called dreamy young man went on to win the very first Nobel Prize in chemistry. What do you think matters more in science, experiments, imagination, or a balance of both? What happens when you sprinkle salt into a glass of water? The salt dissolves. But then what? Is it just a simple mixture, or is something changing at the molecular level? This was the very question that consumed Jacobus Henricus van T. Hoff. Solutions, just a mixture? In the mid-19th century, scientists had a solid grasp of gases. The ideal gas law, connecting pressure, volume, and temperature, was already well established. But what about a grain of salt dissolving in water? Or sugar melting into a liquid? Or medicines mixing into the bloodstream? The microscopic balance behind these processes was a complete mystery. A thought-provoking question. Have you ever wondered why salt water freezes more slowly than pure water? Or why eye drops don't sting when they touch your eyes? Van T. Hoff's groundbreaking idea. Van T. Hoff's revolutionary insight was this. Molecules dissolved in a solution behave just like gases. In other words, dissolved molecules in a solution exert a kind of pressure, much like gas molecules do. We now call this osmotic pressure. What is osmotic pressure? Picture this. Two containers of water, separated by a semi-permeable membrane. You add salt to one side. What happens? Pure water flows toward the salty side. Why? Because the system seeks to balance the difference in molecular concentration. Van T. Hoff was the first to mathematically explain this flow. His equations could predict a solution's freezing point, boiling point, and vapor pressure with remarkable precision. Why was this a big deal? This discovery unlocked a deeper understanding of Why eye drops must match the osmotic pressure of your eyes. Why 4 fluids need the right salt balance to work with your blood. How plants absorb water through their roots. How the human body maintains its delicate water balance. What about living cells? Thanks to Van T. Hoff's theories, scientists could finally answer a profound question. Why don't cells burst or shrivel up and die? It's because the fluids around cell membranes move according to osmotic pressure. And that's not all, chemical dynamics. Van T. Hoff didn't stop at solutions. He also explored how reactions progress over time and under what conditions they reach equilibrium. His 1884 book, Études de dynamique chimique, became a cornerstone of modern chemical kinetics. Another thought-provoking question. Ever wondered why homemade pickles start smelling sour after a few days? That's chemical equilibrium at work. In short, thanks to Van T. Hoff's breakthroughs, scientists began asking not just did a reaction happen, but how and how fast did it happen? Chemistry transformed from a static field into a dynamic, calculable science. Once upon a time, chemistry was just about mixtures, substances, and color changes. Then, a scientist stepped forward and asked, but why do these reactions happen? How fast do they occur? And when do they stop? That scientist was Jacobus Henricus van T. Hoff, and with him, physical chemistry was born. Chemical dynamics, reactions in motion. One of Van T. Hoff's greatest contributions was unraveling the dynamics of chemical reactions, how they behave over time. In 1884, he published Études de dynamique chimique, Studies in Chemical Dynamics, the first systematic work in this field. The book tackled bold questions. How fast does a reaction occur? What factors influence its speed? When does a reaction reach equilibrium? How does temperature shape the process? By transforming these questions into mathematical models, Van T. Hoff empowered scientists to predict and control reactions with precision. Can reactions be explained with equations? Absolutely. Van T. Hoff pioneered the development of rate equations for certain reactions. For example, rate equals K, A, B. With formulas like this, chemical processes became quantifiable, measurable, and predictable. This breakthrough sparked a revolution in fields like the pharmaceutical industry and materials science. At what temperature does a reaction proceed fastest? How long does it take for a drug molecule to take effect in the body? Chemical equilibrium, that never still balance. Another cornerstone of Van T. Hoff's work was the concept of chemical equilibrium. Today, we understand that when a reaction reaches equilibrium, forward and reverse reactions continue, but at equal rates. This state is known as dynamic equilibrium. When this idea merged with thermodynamics, physical chemistry soared to new heights. Van T. Hoff put it beautifully. When a system reaches equilibrium, nature isn't silent, it's simply balanced. What exactly is physical chemistry? Thanks to Van T. Hoff's work, chemistry was no longer just an experimental field. It became a science explained by the laws of physics, modeled with mathematics, and capable of precise predictions. This new discipline? Physical chemistry. Alongside pioneers like Ostwald and Arrhenius, Van T. Hoff laid the foundation for this field. Today, chemical kinetics, thermodynamics, quantum chemistry, all of it rests on this groundwork. Does science become more magical or more mundane when we can describe it with mathematics? December 10, 1901. Stockholm, Sweden. The world gathered for the first time to witness the awards established by Alfred Nobel's will: physics, medicine, peace, and, of course, chemistry. Why was the prize awarded? The Nobel Committee declared, for his discoveries in chemical dynamics and osmotic pressure laws, and his extraordinary contributions to the theory of solutions. What did this mean? Solutions' behavior could now be predicted with numbers. Reactions were no longer just happening, they could be measured and controlled. Laboratory chemistry had transformed into a predictable science. A Nobel marking a scientific shift. What was the most striking aspect of that year's award? For the first time, chemistry was honored not for identifying pure substances, but for understanding how matter behaves. The Nobel Prize wasn't just for discovering elements, it celebrated molecular behavior and mathematical modeling. Van T. Hoff's award symbolized chemistry's evolution, from memorizing formulas to analyzing systems. What do you think? Is chemistry today still about memorization, or is it an art of understanding? Share your thoughts in the comments, let's discuss. The ideas Van T. Hoff introduced in the 19th century still pulse through the four fluids in our veins, the roots drawing water from deep within the soil, and even the gases dissolved in our atmosphere. In medicine, the salt content of four fluids is calculated using his osmotic pressure equations. In botany, plants' ability to absorb water is explained by his solution theories. In pharmaceuticals, the rate at which molecules dissolve and enter the bloodstream relies on his kinetic laws. In climate science, the dissolution of gases in water and atmospheric reactions are predicted using his molecular models for solutions. In education, his equations continue to be taught in high school and university textbooks worldwide. He may no longer be with us, but his formulas, ideas, and visionary contributions to science still shape our world. What do you think is a scientist's greatest legacy? Share your thoughts in the comments. In today's world, science is almost invisible. Our phones, medicines, and food, they all rest on scientific foundations. Yet some of those foundations were laid by one man's curiosity about solutions. What everyday phenomenon do you think could one day spark a discovery worthy of a Nobel Prize? Science continues to forge ahead with the same relentless curiosity. Could we one day fully control chemical reactions? Is it possible to develop ultra-fast-acting drugs? Are new biotechnology revolutions just around the corner? History writes the names of bold scientists in golden letters. Perhaps one day, your name will be announced at a future award ceremony. If you want to join us on this thrilling scientific journey, don't forget to subscribe and turn on notifications. Who knows? Maybe we'll witness the next big breakthrough together.